All right. So someone was asking how I was doing. How are you guys doing? Doing all right? How many of you feel like you got COVID or the flu or something that first week of class? Fair amount of people. I felt like it was like, all right, got it out of the way. We're good for the year. So hope you guys are better. Hope it's you can manage to avoid it or be asymptomatic if that's ideally, but here we are. So I thankfully I'm feeling absolutely better. Had a bit of a brain fog this morning just teaching class at 9 a.m. Sometimes my brain just isn't quite awake, so I should have maybe had some coffee, but I'm feeling good now. So we're going to pick up where we left off last time here. Finish up going through this chemistry refresher kind of deal, talk about the basics of why we care about drinking water, touch on that just a little bit, and from there go into our first really technical topic in terms of treatment components, and that would be sedimentation. Okay, so we left off talking about pH and the whole P there acting as some sort of operator, meaning we're taking the negative log of whatever that is. So P of H is the negative log base 10 of the H concentration. And that's going to be in the brackets, so that means it's the negative log of brackets H plus, giving us some quantification of how many moles per liter of H plus are there in solution. So this is the P here is just meaning it's a negative log. And what we took a look at is, well, for water, we know that the pH range, typically we think of it going from 0 to 14. And if we think about it in terms of what that realistically means, is we're never going to have less than 10 to the minus 14th of either H plus or OH minus. And that can come out, that's why our pH range goes from one to the other. So if you had practically no H plus at all, like the minimum you can possibly make in a normal solution, it's going to be 10 to the minus 14. And that means that you pretty much have 1 mole per liter of OH minus in that case. The reason here is because the product of H plus times OH minus has to be 10 to the minus 14. That's just a known value. That's what our equilibrium constant for water, Kw here, that's how we define it. And we're treating water as if it's a liquid, meaning we treat it as just a concentration of 1. That's just the way we do it. And so with that, we can know, if we know the H plus, we know the OH minus. So if we know the OH minus, we know the H plus in a typical water solution. So this is a very convenient and important relationship for all things pH. And this is the same way it works if we're going to do something in the future, and spoiler alert, we will. When we take a look at, for example, bleach, HOCl minus, or excuse me, HOCl, that's going to be in equilibrium with H plus and OCl minus. So in this scenario, we could take a look and say that the K for bleach, so I'll just call it K equilibrium here, is going to be some value, and it will be equal to the products over the reactant. So we'll have H plus times OCl minus divided by the HOCl. Now, HOCl itself is not a liquid. We dissolved that into the liquid, so this is not 1. This is just as it is. But if you take a look at this, and we'll see later that this happens to be 10 to the minus 7.54-ish, that the equilibrium constant equals that. Then if we know the pH, that means we know the H plus, we should know or be able to find the ratio between OCl minus and HOCl. That's just set. And we talked about that, how we could kind of set some ratio that depends on pH. And so as we change that H concentration, that's the only thing changing in the equation that we are exerting control over, and it causes a change in the equilibrium of these two other things, right? So if we take a slide and move it across the pH slide, it will cause a change in the ratio of these chemicals, right, based on the equilibrium reaction. And that's defined in part by this equilibrium constant, whatever that happens to be. Okay, so we will come back to that when we talk more about chlorination. I wanted to give you this up front. I think I've got a problem in the first homework that kind of gives you some practice with that and with pH in general. Does this make sense to you? Clear enough? All right. Okay, so with that, I want to move on to drinking water. And the very basic way to look at why we care about drinking water, and maybe the historical way, is the fact that, you know, if we have some body of water, we might want to drink from it, right? So we might want to grab a glass of water and drink that water. Now, if you're thinking to yourself, well, I would never grab water from the local bayou, the LSU lakes, or Mississippi and drink that, that would be gross. Well, you're onto something, right? It's maybe not safe to just grab water and drink it. That's because there's some stuff upstream. And in particular, what we would typically care about is any time we have a system where perhaps something is being added into the water that we don't want to drink, right? And so our first barrier to what we would call the fecal-oral route of transmission for pathogens, it's like the very fundamental thing. You don't want to get sick by drinking the water. We'll talk more about that, you know, when we get to disinfection, but it's pretty fundamental, right? That's not good to drink. So we have a barrier here to say, okay, well, we're going to have wastewater treatment to help prevent that, or make it less likely that pathogens are making their way there. But we don't necessarily have wastewater treatment for all the little animals out in the wild that also happen to be adding to our water supplies, right? So there's quite a few reasons, and you can see why I'm an excellent artist here and probably won't continue to draw things for you. But you can see why we need another barrier, right? And this is our drinking water treatment. So this would be potable water treatment or drinking water, whatever you want to call it. Okay, so we are now motivated by the stick figures to treat our drinking water, which was already obvious. But this route of transmission sounds pretty dumb, but it's actually kind of essential. If you had access to water that never ever could have encountered anything's fecal matter, then it's actually probably a pretty good chance it's safe to drink, at least microbiologically. The thing is in our warm-blooded guts, there's bacteria. We like the bacteria to be where they need to be to give us some benefits, help us digest our food. If they get to the wrong places, we have an infection potential and can make us sick until it all sorts itself back out and our body reaches balance again. So we really want things in the right order, and clearly it's upsetting and not a good time when they're out of order. So if there's scenarios where another warm-blooded creature might have excreted their waste containing all that bacteria, we want to avoid that. We want to cook it, we want to boil the water, we want to treat it in some way to prevent that. Okay, so that kind of leads us into where are we getting the water supply? So if you could always take from, let's say, pristine glacier melt, and you could check and make sure that there wasn't a whole lot of, I don't know, contamination from the clouds and the rainwater, whatever was the precipitation, not rain, but snow, whatever was creating the glacier in the first place, if that was clean enough and you could always take that water, yeah, maybe you don't even need disinfection, right? There's no pathway for pathogens to get to that spot. But that's not typically the reality, and so we have to design our treatment based on kind of what the context is. Where are we getting our water? What are the contaminations we expect in the water? And what kind of technology do we need? We can even treat seawater. It's just going to take a lot of infrastructure and energy to remove the salt. Salt is a very difficult thing to extract out of water. You can do evaporation, and that's happening all the time. So you could maybe collect rainwater. You could boil it. That's a lot of heat you have to add, and then you have to cool it back down. You can do something called reverse osmosis, but you have to add a lot of pressure for that, and you have to maintain your membranes and things. It's certainly doable, but there's costs, right? So we generally optimize to try to make our water, we treat it to the level we need, but we also try to do that in the most economical way possible, right? There's also some environmental concerns. Where are you going to dump all the extra salt that you just created, and how are you dealing with that in a way that's not going to harm the ecosystem that maybe you also want to protect nearby? So there's a lot of balance there. That's pretty typical of our environmental systems and environmental engineering in general. So if we take some sort of water source and we maybe want to think about how the engineered water system will look like, a generic picture here for us, where we have maybe a stream, a lake, a reservoir, or a well water giving our treatment plant some water. Well, we'll take that, treat it accordingly to make sure it's protective of our health, and send it along to our municipal systems, so our homes for domestic use. Sometimes this will go to industrial use. Now that could be anything you could consider, I suppose, even the local McDonald's, a industrial user in a sense. But also, it could be any other type of industry may buy water from the municipal plant. In Baton Rouge, we tend to have well water that doesn't require a lot of treatment. It's good quality well water here. And we actually have a little bit of controversy because industry also says, well, we'll dig a well and tap into the same water supply and use that because it's the cheapest option for us to use. We need good quality water for our facilities so that they don't get mineral deposits or any other issues. It's pretty clean, so it's a great cheap source of water for them. However, it turns out that the groundwater supply we have, there's what we call an aquifer, and on the southern end of Baton Rouge, there's deep in the ground, there's sort of almost like a protective layer that separates a couple aquifers, and on the other side, it happens to be a very salty aquifer. It's not actually seawater, but it's just very salty groundwater. And if we're pulling down on or withdrawing so much of the nice fresh water that we have access to, it actually is starting to cause some infiltration across that barrier. There's some spots where it can come across. So there was some concern over saltwater intrusion into our nice groundwater aquifer. So there's lately been some controversy in how to govern the situation, and maybe asking the industry to instead get their water from the Mississippi and treat it to the levels they need. So just a little microcosm of the current policies, politics, or dynamics for water supply here. So anyway, we'll use that water. We will then flush it down the toilet or whatever, and that will go into our sewer system and eventually reach our wastewater treatment plant. Now, sometimes industry may also elect to pay to hook up to the sewer and send their wastewater there. Some industries that might be fine. Maybe you have a tissue, like a fiber recycling plant, recycling a bunch of cardboard to make tissue paper or something like that. They're going to have a lot of fibrous, carbon-containing stuff in their wash solution, and there's a good chance that typical microbial stuff can eat a lot of that and create just bacterial cells in place of the junk that was in there. However, if they have something toxic, then they actually have to pre-treat it before sending it to the sanitary sewer, because if it's toxic to the bacteria and we're relying on the bacteria and the wastewater to do the job, we don't want to kill it all. But we'll talk more about that when we get to wastewater treatment. Last thing is, sometimes people have, or municipalities used to combine the sewer systems, like the storm sewer systems, with the sanitary, the septic, like our actual sewer systems. And that's not a great thing, because when it rains, then if the sewers flood, you're flooding wastewater everywhere. So we generally, as a rule, we're trying to separate now, and you'll see some of that if you ever get into the field, a storm separated sewer system, MS4 or something like that, municipal storm separated sewer system. So hopefully that's the case, and that is increasingly the case wherever. But you see here, this, if we had a river, a stream, something, what we have is some taking in water up here, discharging water down here. And there's two things about that. First, we already talked about, now we're discharging wastewater that might be upstream of somebody else that needs to take water, right? So now they're getting our wastewater. Very obvious that that's what happens with the Mississippi, and why we might be glad not to live in New Orleans, right? They have to take the river water and treat it. Of course, they do treat it sufficiently, or they're supposed to, right? So shouldn't be any issues there. But it might not sound like the best idea. Now, the other thing I want to point out here, if I remember my train of thought, I had something to say. Okay, I lost it, so I'll let you know if I find it. All right, so speaking of the fecal-oral route of transmission, typhoid fever is a good example. This is actually something that is contagious through this route. You know, lately we hear all about the airborne diseases, and we hear about flu, COVID, colds, all that. That's just, you're in the same room, you're breathing the same air sharing, and you know, someone sneezes, oops, there's some people sick. That's kind of just a function of humans being in the environment with one another. And there's not a whole lot we can do about that if we care to be in the human environment with other humans, right? To be actual social beings. Now, when it comes to the fecal-oral route of transmission, fortunately, there's something we can do about that. And unless there's some specific outbreak, like a sick employee at, I don't know, Chipotle or somewhere, then with good sanitation and hygiene, then we can get rid of this. And again, the example, if you have a food or a restaurant place and somebody's working while sick and not practicing good hygiene, that's the thing, right? We need good hygiene to avoid this. So in addition to good hygiene, having clean water is important. So around 1908 is when we first started chlorinating water to drink in the US. And you know, it probably wasn't everywhere all at once that was chlorinating, but we see that around that time, you know, we were also more and more aware of the importance of hygiene, things like that. So over the next 30, 40 years, typhoid fever became pretty much non-existent, and it used to be a very, very concerning disease because it was pretty dangerous. It still exists today. We don't have meaningful numbers of it in the US, but if you travel somewhere, you might need a typhoid vaccine, or that might be recommended because you do well to try to avoid it. And if you have to eat and drink local food and water in a place that doesn't have the same hygiene standards, or there might be more likely to have breakdowns of it, and there's active typhoid, would be nice to avoid that, right? So this is a good example of that dynamic. Okay, so the enforcement, or I guess the legal side of our drinking water comes from the Safe Drinking Water Act, 1974, and it really put forward two kind of standards or categories of standards, which would be toxins and pathogens, as like, here are the things that we need to make sure are not in our water, right? Anything that's toxic, anything that's pathogenic, at pathogenic levels. Then we can kind of categorize this into two dimensions here. One would be primary standards. These are anything that causes a health impact that could be detrimental to somebody's health. So these are enforceable by law. That would include chemical, radionuclides, and microbial. So there's your toxins and pathogens, right? So there are other recommended regulations. I think I probably mentioned this in our first lecture. that are not actually required, right? We have aesthetic concerns. We don't usually want to drink brown water or orange water, although I see somebody with orange water, so it's not out of the question. We might add some stuff on purpose to drink it, but if it's coming out of your tap and it looks orange, we might be a little concerned, right? And we might not like to shower in that or wash our clothes with orange water. There's a lot of things that we wouldn't like, and so there's pretty good reason for the public's consideration why a municipality would want to treat their water to meet these secondary standards. Other things would include the taste, the odor, even temperature. Turns out oxygen dissolves better in colder water, and oxygen tends to impart a nice taste to water. Changes it slightly. So if you ever find yourself drinking lukewarm water or even slightly warm water, you might be kind of grossed out by it. You'd rather it actually hot or cold. And part of that is that it tastes better when it has a little more oxygen in it, which it would be colder water. Hardness is another thing. That's kind of mineral deposits. I think I talked a little bit about this already, but if you take soap and you have very hard water, we'll see why actually probably next lecture. But what happens is it prevents the soap from making bubbles very well if there's a lot of minerals in it. Whereas if it's very soft, it kind of prevents you from getting the soap back off, because or at least it feels that way, because it actually makes a barrier of water between your particles and a surface. And so water hardness can change the way soap works. So you need more soap if you've got hard water. And it can also, hard water has a lot of mineral content by definition, and then would cause mineral scaling, like deposits around a sink, things like that are just not as pleasant. Can also be a problem for industrial applications. So we won't talk about it for you because I'm not going to torture you that much with chemistry, but water softening takes a chemical procedure, uses a lot of pH changes, adding some stuff, and we can actually remove a fair amount of these minerals it doesn't matter if the minerals are there for health reasons, but we like to have fewer minerals. So here's a map showing in the US kind of the typical hardness of water. This is probably groundwater. I don't know, maybe it's surface water. But if you take a look, it might be fun to look at where you've been, right? So I grew up in northern Georgia, somewhere around here. I lived for a couple years in the middle of Michigan, and now I've been here the past 6-7 years. So in Michigan, we had some harder water, but otherwise, generally, I've encountered pretty soft water. So I don't know if any of you noticed that impact, lived somewhere interesting that had pretty hard water, or never noticed at all?
My mom always comments on my water when she comes visit me, but she only lives an hour away.
Okay.
But she always says because I'm from Morgan City, so the water is so much softer up here.
Okay.
But I don't know.
Yeah, no, that could very well be the case. And if you look right here in Louisiana, it's like there is a threshold. So depending on where you're getting the water from, can make that difference, and it could just be an hour drive to cross a boundary like that. Yeah, so if you haven't noticed it, maybe next time you travel somewhere, just think about, or if you're washing your hands or something, just think about is this coming off easy? Is it making a lot of bubbles with just a little bit of soap? Or is it hard to even get any sort of soapy action? Okay, so when we think about starting a drinking water treatment, we're going to take a look at maybe a typical design of surface water treatment. Now, sometimes groundwater is clean enough where you kind of just disinfect it and send it along. Of course, you're going to monitor and things, but sometimes you don't require all of this. But this is a pretty generic, if you're going to treat some surface water, it will look something like this. Maybe you have to add something special if you have a particular contaminant that's hard to deal with. So we'll take some sort of surface water. We'll send it through a screen chamber, a bar rack, something like that. Something to, stop fish from swimming in, stop the basketball that's floating down the creek, from getting in, and all that stuff. A grit chamber to try to remove the large like, or little small pebbles or large grains of sand, something like that, that could probably harm your pumps, things like that, your plumbing in general. You want to try to get rid of that stuff as best you can. And then the next step, and that's all pretty mechanical and not super interesting. There's devices for it, I'm sure, but it doesn't take up a lot of space or energy. It's sort of just a physical screening sort of process. So then we get to sedimentation, which also is a physical process and is at first glance pretty simple. And that's what we'll talk about today. And sedimentation, we're going to use gravity because gravity is pretty cheap and all that. So we'll sediment the larger particles. They'll fall out of solution as best we can, collect those and send that to kind of a sludge. That'll be like a sludge that we can squeeze the water out of and send it to a landfill. The next thing is we're going to actually send it through a couple processes to improve sedimentation and then do sedimentation one more time. So we're going to do sedimentation a couple times, and the processes in between are designed to cause the smaller particles that we missed the first time to start sticking together and flocculating in order to settle out during the second sedimentation chamber. From there, we typically filter it in some way. There's still going to be some particles, particularly bacteria, things like that really weren't effectively removed. So we might try to get those with filtration just to kind of clean it up from particulate matter standard. And then, of course, there's going to be some bacteria that escape that too, and certainly a lot of viruses that are much smaller than bacteria. No chance at sedimenting those unless they happen to be sticking to a particle. So we'll disinfect it, perhaps add a bit of corrosion control if we need. We'll talk about that when we talk about the Flint water crisis. And then send it through the distribution system. Now, the distribution system itself, we tend to consider as a part of our treatment because we design that so that it keeps enough chlorine to prevent any pathogens from repairing themselves or from entering from maybe a leak in our pipes or something. And in fact, one of the reasons we keep high pressure in our pipe systems is to make sure that if we do have a leak, because it's going to happen, that the water is forced out and not let in. So there's a lot of reasons we like to have high pressure in our water because we like to have have hot showers or just showers in general with some pressure. Wash our hands. We like to be able to do that even if we live up on a hill, to be able to have water pressure up there. So there's a lot that we design our systems to have pressure for, but in particular, we want to prevent intrusion of anything that might be contaminated into our system. So that plus firefighting needs a lot of water are two of the major reasons we actually care a lot about our pressure in our distribution systems. All right, so we're going to start with sedimentation then, and that'll be the next set of slides. All right. So for sedimentation, we want to use gravity. Pretty obvious, right? It's cheap, it's reliable, pretty easy to predict. It's not typically going to change much, or we'd have some other problems if it did. Maybe if we had to treat water on Mars or the moon or something, we might have to think a little differently or plan accordingly. But for our own sake, what we can do is consider a scenario where we can make a few assumptions and make use of gravity to remove our particles. Okay, so this will be something that we do in drinking water treatment and in wastewater treatment. So we're going to use it in both contexts. Like I said earlier in the semester, a lot of the things we learn are actually applied to both, and I'm just going to introduce this one first here. Start off the semester with some of the physical processes. You'll notice we go kind of physical to somewhat more chemical to then biological kind of at the end. So using gravity is definitely a physical process, and what we'll see if we think about it is we'll have some force of gravity that will be opposed by some buoyant force. So how much mass of water are we displacing? If you've ever tried to take a beach ball and submerge it underwater, you've encountered a buoyant force, right? There's technically some gravity pulling that ball down, but it's certainly overpowered by the buoyant force. Then, assuming we have some acceleration due to the gravity and a higher density of our particle than the water, so that we can actually sediment it, and it's going to sink, then we have an opposing force of drag. So we've got a drag force and a buoyant force pointing upwards, opposed by a force due to gravity. Now, there are a couple exceptions. Sometimes people will add in small bubbles to a system like this and cause flotation on purpose, and essentially it's a sort of dissolved air flotation, I think is what they call it, and they just do sedimentation in reverse. They float the particles and separate the particles that floated instead of sinking them and separating the particles that hit the bottom. We're not going to deal with that, but just so you know, if we did it that way, then the drag force would be reversed, right? Because it's just going to oppose the motion. So the point here, though, is that we want to find the terminal velocity for a given particle. And we're going to make a few assumptions, including that we're going to assume that even if the particle looks maybe like this guy, we're just going to assume that it's actually a sphere. You know, it's not truly realistic, but it's a nice simplifying assumption. So we can assume spherical particles. We can also assume that all the particles are the same size. That's also not true, but for a practical standpoint, if we're trying to design a system to remove a particular type of particle or a class of particles that are about this particular size, it's pretty useful, right? It's fairly reasonable. So we're going to assume all particles are equal sized. We'll also, part of this we'd also be assuming for the moment that they're not sticking together and becoming larger size. We're going to intentionally do that later, but then when we actually do the math for the sedimentation process in that moment, we're going to assume that process has stopped and reached all the same size. Okay, so with that, then we should be able to find a terminal velocity, and we should be able to do that by setting up a force balance. And I'll put up another slide with all these terms elaborated on, so you'll have that in place. But basically, we have the force of gravity is the mass of the particle times acceleration due to gravity. The buoyant force is the mass of the water displaced by the particle times the acceleration due to gravity. And then the force of drag would have something to do with the area of the sphere as it's traveling through the water at some velocity. So that would be 3 times the dynamic viscosity of water times pi times the velocity times the diameter of that particle. Now, the only thing I'm going to highlight just now is that we have a velocity term there, and we're going to set up our force balance and solve for that velocity term as a way to say, okay, we have the system, here's our velocity. Okay, so I'm just going to walk that through you so you see where this is coming from. It's not super complicated, but it's kind of nice to walk it through to see. So lots of assumptions, of course. Here are the definitions we're talking about in these systems. And one other thing I didn't mention, for these forces for the gravity and the buoyant force, it's not very easy to weigh one particle, especially one of these really, really small particles. In fact, that's nearly impossible, even with our modern technology, to weigh something like that. There's probably some ways we could get an estimate, but it would be very, very difficult. So what's much easier to do is to find the bulk density. If you were to use a filter to separate those particles and then weigh a whole bunch of them and compare that to how much water they're displacing, so what volume of particles versus their mass, that's much more possible. And you can get some idea of how dense the particles are. Some other ways to do that, including sedimentation, you could just make some observations to check. The other thing that's pretty easy to do is to measure their size. So we have pretty cheap reliable methods to get a good estimate of how big are these particles. So instead of using the mass times the gravity, we're going to use, so this would be mass times the gravity. We're going to say this is going to be the volume times the mass per volume times gravity, right? So the density is just mass per volume. And so if we take the volume of the particle, multiply it by the mass per volume of particles, then that's just giving us mass. So that's where we get these terms here, where the rho p is the density of the particle, and the rho with no subscript is the density of the water. That's all defined over here on the left. Okay, one thing I'll note here is for this calculation, we're going to keep everything in kilograms, meters, and seconds. We could convert to some other unit, but since our dynamic viscosities are typically given in kilograms, meters, and seconds, acceleration due to gravity, we should remember this is 9.81 meters per second squared. We just already have a lot in meters and seconds and kilograms, so we're going to keep it that way. So whenever we solve a problem for finding a sedimentation velocity, a lot of the problem will just be converting the units accordingly and making sure we're set on all of that. We'll do an example problem today. Okay, so for the force balance, we're going to set it up and say, here are our force equations. We're going to take the force of gravity and define that V times rho, so the volume of the particles times the density of the particles times the gravity, and we're going to set that equal to the buoyant force, so the volume of the particles times the density of the water they're displacing times the gravity, plus this force of drag. This is the drag force on a sphere that's moving through a liquid. We're just going to take it for granted that the book is right on that. Times this velocity term that we're going to solve for here, times the diameter of the particle. Now, one thing you'll note is we have volume and diameter, and we can get a volume in the form of diameter. And double check me here, but I think this is 1/6 pi pi diameter cubed. It's like 4/3 pi r cubed, right? And it's in terms of a diameter that should give us 1/6 pi diameter cubed. Someone Google that for me, check it. Pretty sure, but. So we can basically get the volume in terms of the diameters, is my point. Anybody confirm? Gonna make me do it?
Yeah, that's it.
Okay, great. Thank you. Okay, so with this, we really want to solve for the velocity term, because that's what we're interested in. We need to know how fast these particles are settling. That's going to tell us how we can design our system to settle them in time before the water leaves the sedimentation chamber. So I'm going to put the, I'm going to subtract this buoyancy term from both sides. I'll also just go ahead and rearrange a little bit. So I'm going to put Vs on the left side times this 3 mu pi dp. So just putting this on the other side, swapping them around. And I'm going to subtract this buoyant force from both sides. So that's going to be the force of gravity here minus the buoyant force here. And so we have this equation. Now I'm going to go ahead and divide everything by the 3 mu pi dp. And I'm also, before I get quite there, I'm going to factor out the volume and the gravity here. So I'm going to say the volume of the particle times gravity times this density of the particle minus the density of the water, and divide all of that by the 3 mu pi dp. So now, if we take our our volume term and put it in terms of the diameter, we can say that's going to be equal to, instead of the volume, we're going to put diameter cubed, but we have a diameter at the bottom, so that's going to become, I'm just going to write it how the book has it. So we're going to say G times the rho of the particle minus the rho of the water times dP squared. That's coming from the volume as a cube, but dividing it by the dP that was on the bottom here. So that will get canceled. And on the bottom, we're going to have the pi over, well, the pi on top will cancel with the pi down here on the bottom, so no pi anymore. We'll have it divided by 6, and we'll multiply that by the 3, so we'll get 18. And the only thing left here is the mu, the dynamic viscosity of water. So this is our derivation of Vs. You're going to be given this equation on your exam sheet. I just wanted to walk you through kind of how that works so you can see where this is coming from. One thing you'll notice is the diameter here. If we are able to change the diameter of the particle, that's going to change how fast the particle is sedimenting quite well, right? By a square, power of 2. Whereas if we were just to change the gravity, that would change things a little bit. We can actually do artificial changes in gravity by centrifuging things, causing particles to sink faster. Use that a fair amount in a lab. You're just essentially inducing an artificial gravity, causing sedimentation. You can change the density, perhaps, of the water just a little bit by changing the temperature. So if you're doing sedimentation during the winter versus the summer, that might actually be a little bit important. You could also maybe change the density of the particle. But none of those changes are really going to make as big of an impact as changing the size of that particle. So the larger the particle, the faster it will sediment. Okay, so now we have some idea of how fast the particle is going to move in the water. How do we actually put that into a reactor? So there's two generic types of sedimentation chambers. One would be kind of a rectangular system where we just have water flowing through. And by the time it reaches the end, if the particle has sunk to the bottom, then it's removed. It'll stick to the bottom. Then we later will scrape all the particle junk and collect it, maybe have a little vacuum sort of thing. We have some mechanical way to collect that stuff off the bottom. And meanwhile, continuously the water will be collected off the top of the water into the next chamber for treatment. Sometimes we'll have a circular system. So we'll have a kind of a radial direction of flow where the same thing is happening. Water is traveling, particles are sinking. It's laminar flow, so it's nice and smooth, steady, and particles are just sinking along the way. And if they reach the bottom before the water overtops the other side, then we say the particle has been removed. So taking a cross section. So if we were just to take, maybe this is just a sort of a cross section of that, or a cross section in our chamber here, we can take a look from the side view, of cross-sectional view of that, and say, well, what's happening is we have some particles that are sinking over time. And if it hits the ground, perfect, we've removed that particle, okay? And so one thing you'll realize is the particle that starts at the top is really kind of our design criteria, right? That's the particle we're trying to remove. Everything below that, given that we've got laminar flow that's not turbulent and stuff, not mixing it, everything below that, if we sediment this one, all the others will sediment as well. So as we'll see in a moment, we can say we have a critical design velocity for the velocity component downward that's required in order to achieve that one to get settled. Okay, so let's focus in on that a bit. If we have some particle, we'll put a particle here for the moment. We can say we've got some height to that particle. We also have some height of the chamber as a total. And as we think about which particles we need to remove, maybe this guy is going going like this, reaches the bottom. Again, this is a cross-sectional view. So height is the y-axis. We could draw sort of a hypothetical depth in here that would be maybe the width of the reactor and have a length here. So if this is rectangular, or we could spin this all around in a radius and that would be a circular reactor. So at any rate, this is the cross-section. If we want complete removal, we can consider the height of the particle when hp, the height of the particle, is equal to the one right here, right? So I guess we would call this hp2 or something. You know, if this is hp equal to h, whereas we could have some other particle heights. This is the case where we can design it for complete removal. Again, if this particular particle intersects the bottom before it leaves, or right at that diagonal, right? Okay, so then, as we think about how fast this particle has to move in order to not escape, then we can say that it has to travel hp distance, or really h distance, in the time it has in the reactor. So the time it has in the reactor is the volume over the flow rate, right? That was our definition of the hydraulic retention time. That's just volume divided by the volume per time, gives us the time in the reactor. So when we talk about h, this height has to be traveled in the amount of time it takes for the sedimentation velocity, this height will be the distance it travels given the velocity it's traveling times the time it has to travel. So Vs times theta. That's the time we have. You know, this is just saying a velocity, or the distance equals velocity times time, right? Very obvious or rudimentary thing, but what we're doing here is saying we're setting it so that this is the distance that we have to do in order to get that particular particle to settle. Now, when we have the scenario of this highest particle and it is just barely removed, we call that V naught, the critical settling velocity. In this case, equals Vs. So I'm going to call this Vs1 for a moment, just to make a bit of a clear difference. So if we had Vs2 here, Vs1 there, and Vs3 here, only one of those is exactly the same as our critical settling velocity, and two of them will have all the particles removed, right? This Vs3 here, clearly those particles aren't getting removed. They're not traveling downwards fast enough before the water leaves. The water, again, is flowing in this direction. So, as the particles are going, we will define a critical settling velocity based on the design of the reactor itself, and we'll compare that often to the particular settling velocity that we might have. So if we have a condition where, again, I'll draw a few cases here. We'll do Vs3, we'll just call this V, we'll do V naught, the critical, V1 and V2. So if we have a particle traveling equal to V critical, that by definition, all of the particles will be removed, right? So if V naught equals Vs, all removed. And then we could say since Vs1 is faster than V naught, we then also have all removed. And since Vs2 is less than V naught, we would say not all of them are removed. Now, you might notice that we may get some removed in the Vs2 case if we are to draw a similar line, similar velocity starting here. We could also call that Vs2, and some of the particles will be removed. Okay, so we'll come back to that and describe that mathematically in a moment, but just keep an eye on that because that's something that can definitely happen for us. Okay, so there's one other concept I want to introduce here, and that is how do we connect our critical settling velocity to the actual design of the reactor. Okay, so in reality, we'll have some reactor, and it could be a spherical one or a circular one, excuse me, like that, or it could just be a rectangular one where we'll draw it and say this has 3 dimensions, the length, a width, and a height. And we are really, again, interested in that particular one that makes this diagonal as our V naught. So, and really the V naught technically is that downward component, right? So in order to relate the V naught to the flow rate and the size of this chamber, we can say that our V naught is equal to the flow rate divided by the area of the basin. In this case, area of the basin would be length times width. And the reason we can say this is because we've defined V naught as the exact amount of time to travel from the height to the bottom in the amount of time it spends in this reactor. And so that means if we take the flow rate, which is, let's say, cubic meters per second, and divide that by square meters, that yields us with meters per second. And if you stop and think about it a moment, you've got the water flowing through, and if you give it a wide area, that height that it would have to travel kind of shrinks. Like if I were to pour my bottle of water on the desk here, it would start spreading out, right? But if I poured it into this little channel here, it would channelize and go a longer ways, and if it was deep, it would be deeper, right? So depending on the area that it's spreading, that's at play here. So it's actually that area over which we're spreading out the water is kind of what's spreading our flow rate out. And ultimately, the only thing left is that downward component that we call V naught. It's a little, it's a little counterintuitive to think that in our equation for V naught, the height doesn't matter, but it's captured within the flow rate. That's why it doesn't matter. So this is a definition. I don't think I have it on your formula sheet, so do remember this. It's kind of by design. The distance it travels, given some time it travels, is set up that way. We could also consider the fact that, this is distance over time. So this would also look like height over theta. Should be V naught. And if we look at it that way, the height over theta would be height over V over Q. So we'll say length times width times height divided by Q. And so we could say, well, those heights will cancel, the Q will come to top, so that'll be Q divided by length times width. Right? So a few ways we can identify why this works and how we get there, but essentially that's the target, is this particular parameter. Now, as we move forward with design, what you'll notice is that V naught is kind of the design, Vs is an observation or something we calculate given some observations. Sometimes we will design according to some particular particle. And we'll do that because we have it in mind to remove that particular particle. And so we will sometimes set V naught equal to the Vs that we really need to remove. We decide we have to remove all of the 0.1 millimeter particles and everything larger. So we're going to set our V naught equal to the Vs of that particular case. So when you solve problems, and we'll do one in a moment, keep that in mind that we've got these two velocities. One is for the design, and sometimes we'll design that based on a particle, but the Vs is always that sedimentation velocity that we're observing or calculating. Okay, so let's give it a shot. This is example 6.1 in our book, and we're going to do silt removal in a clarifier. It says we have a drinking water treatment plant that uses a circular sedimentation basin. So real quick, we'll assume that's kind of some sort of circular basin. Water's going to move out. We'll have some radius or maybe a diameter given. And in the case of a circle, instead of the area being length times width, it's just going to be pi r squared, right? Or I guess you could say pi d squared divided by 4. Okay, so we're given a circular sedimentation basin to treat 3 million gallons per day of river water. That's, MGD is an acronym for that. And it gives us conversion to get us back to meters and seconds right here. After a storm occurs upstream, the river often carries 0.01 millimeter silt particles with an average density of 2.2 grams per centimeter cubed. The silt must be removed before the water can be used, and the plant's clarifier is 3.5 meters deep and 21 meters in diameter. So we also have a height to this. As you see what I'm doing, I go ahead and start drawing it as soon as I'm getting information. Definitely encourage you to do that when you encounter a word problem. So draw it up to make sense of it and put pieces where you see. Okay, the silt must be removed. Got this 3.5 meters height, 21 meters diameter, and the water is 15 degrees Celsius. So that means when we use this lookup table for anything we need, we'll look across at the 15 here. I'll go ahead and highlight. We're going to need this density and this dynamic viscosity. Okay, so part A says, what is the hydraulic detention time of the clarifier? That's theta. And then part B says, will the clarifier remove all of the silt particles from the river water? And as a little reminder, when it says, will it remove them, what we ought to be thinking about is V naught compared to versus Vs. Vs. I was writing Vs to make a comparison like versus. So I'll just do that. So we're going to compare Vs to V naught in some manner to answer that question. All right, so take 5 to 10 minutes on that. See where you get, and I'll join you partway through for part A, and then give you a few more minutes and finish out the problem with you. Feel free to work together, ask me questions. Just get your brains moving on this to make sure you kind of understand the type of approach you'll need here. Okay, so part A, hopefully you were able to take a look. I just started writing some stuff out here on the a little bit more room. You can get the area of the basin with the diameter given. That should be 346 square meters. Means the volume would be 3.5 times that, so 1212 cubic meters. And we could calculate the flow rate given the information with a 3 mgd. The conversion should be 0.1314 cubic meters per second, giving us a theta of 9226 seconds. We'll go ahead and leave it in seconds. You know, it's just going to be convenient to keep everything in meters, seconds, and kilograms, even though the particles are not going to be anywhere near 1 meter per second travel speed. They're probably going to be some small fraction of that, right? But that would be part A. I'm going to go ahead and start sketching up part B. Take a couple more minutes if you need, or follow along while I do that.
What'd you get as the radius?
Radius, I would take 21 divided by 2. So 21 meters is the diameter. So 10.5.
Is the Q from the 3 million gallons per?
Yes, so we got 3 million gallons per day, and then multiplied by this 0.0438 cubic meters per second. What they're saying is here it says million gallons per day stands for million, blah, blah, blah. 1 mgd is equal to 0.043. So we multiply that 0.043 by 3 because we were given.
And what does
Q is flow rate. I'm so sorry. Yeah, that we'll be using that all semester, and I forget to properly introduce it sometimes. Q, we're always going to say is flow rate. I should have been clear on that. This capital Q is pretty much always flow rate for our class. I don't think there are any other exceptions. And I'm willing to bet everybody's very thankful for that clarification. So thank you.
So the hydraulic detention time is V naught?
The hydraulic detention time is theta. That's going to be up here. That's Q over V. Excuse me, V over Q. All right, so let's take a look at this. I went ahead and did a fair bit of this in Excel, in case you're curious here. But essentially, the primary tricky part of these problems is really just going to be making sure your units are consistent and correct. So we need mu in kilograms meters per second. And as I told you from the first class, there is a built-in trick here, and it's not meant to trick you, but maybe a good reminder to pay attention to your units. And that is that the units for our dynamic viscosity has a 10 to the minus 3 built into it, right? And so when we pull that number there, this is probably the most common mistake, is to forget to put the 10 to the minus 3 into our calculation right here. Yeah?
For my BX, I got 5.75 times, like, a huge number, like, way bigger than that.
Okay, so then the other possibilities here, another one would be to take the mu and let's see if we can find that, right? So we can take the mu here, and actually I forgot to write one of these here. The mu, excuse me, not the mu, the rho p, 2.2 grams per centimeter cubed. We need to convert that into kilograms per meter cubed, and as a kind of a cheat code, you can generally assume that if our particles are settling, it should be at least the amount of density as the water. Should be actually more than. So it shouldn't be like thousands and thousands of times, otherwise it's just like shooting through the water, right? So it's going to be on the order of 1,000 to 2,000-ish. So you can almost always say that this 2.2 should become about 2,200, and if you do the math, convert it here, convert it with the cubed, the 100 conversion, that should get you to 2,200. Now the other thing, which is probably, I'm going to bet, and I forgot to write this up, is the diameter of the particle here, we were given as 0.01 millimeters, and I have to confess, I did this in my mind wrong this morning when I taught my other class, so I gave them the wrong solution. But when I was a little more careful about it just now, or maybe it's just not morning anymore, we can convert this and say this is going to be, if we convert that to meters, that would be 0.01, except we're going to add 3 here. That many meters, so that should be what? 1, 2, 3, 4, 5. So 1 times 10 to the minus 5th meters. Then we're going to put that in and square it here. So was that the issue, the conversion? Because if you don't convert that and then you square it, certainly there's going to be a big number change there. So it's a good way to check to say, hey, is this a very small fraction of a meter per second? Because it should be. Now, let me just conclude like this and say this 5.75 times 10 to the minus 5th is smaller than the design, meaning we're not going to get everything settled, right? So not all settled. All right, have a good weekend. We'll see you on Tuesday.